Hello and welcome back to your Chem 4 lecture. We are moving on in chapter 14 to talk about esters. Note this is different from the compounds that we talked about before, ethers. This is esters. So we'll look at the structures here on the next slide. But first, like a little backstory on esters, is that they're one of the most useful formulations of products for medicines in particular. A lot of useful medicines can involve carboxylic acids, but carboxylic acids irritate the stomach lining. For example, salicin. So there's a product from willow tree bark that naturally occurs that's really good for pain relief. And so people knew and brewed tea out of willow bark and would use that to ease pain. Well, as it turns out, that salicin converts to salicylic acid, which is responsible for the pain relief, but also it also irritates your stomach lining because it's a carboxylic acid. However, industrial chemists realized if they take the salicylic acid and turn it into an ester instead, what happens is you prevent the stomach irritation, yet you retain the pain relief properties. And this led to the development of acetyl salicylic acid, which is known as aspirin. So we'll talk about that here in a little bit. So what are esters? Esters are made from the reaction of a carboxylic acid and an alcohol. Esters are frequently found. They tend to be nonpolar, so they dissolve well in fats and oils. And it's also esters that are responsible for various fruit flavors and aromas, including bananas, oranges, and strawberries. So carboxylic acid, for example, we know that has a carbon double bonded to an oxygen with a single bond then to a hydroxyl group, the OH group. An ester, on the other hand, does not have the OH. Instead, it has an oxygen bonded to a carbon. So it's almost like a combination of a carbonyl with an ether, whereas the carboxylic acid is a combination of the carbonyl with an alcohol or hydroxyl. So this is the reaction that I was talking about for esterification. You take a carboxylic acid and you react it with an alcohol in the presence of heat and an acid catalyst. So that's how we would write this. And what happens is basically there's what's called a dehydration reaction, where this oxygen and this hydrogen are going to leave. So this OH group with this hydrogen are going to leave to form water. And this oxygen from alcohol is going to form a new bond to the carbonyl group from the carboxylic acid. So that gives us this setup right here. So whereas before we had ethanoic acid reacting with methanol, now we have an ester that's called methyl ethanoate. That's a little preview of how we're going to name these esters. So for example, you can take ethanoic acid and 1-propanol, and you would produce an ester that's called propyl ethanoate. So ethanoic acid, propanol, and you get this propyl ethanoate. So I'll mention it here, but you probably notice already. The propyl, the first word that covers the ester, is the name of the alcohol in alkyl form. So propanol is a 3-carbon chain, so that comes from propane. As an alkyl group, that's propyl. So that's our first word. The second word, carboxylate form of the carboxylic acid. So ethanoic acid becomes ethanoate, for example. So the carbonyl, or the ester that combines the two, is propyl ethanoate. Okay, but before we get there, go ahead and write the balanced chemical equation for the reaction of propanoic acid and methanol to esterify. This is the esterification reaction that we just looked at. So pause it, give it a shot, and when we come back, we'll take a look at the answer. Pause. Okay, let's walk it through. So first up for the reactants, we have propanoic acid and methanol. Well, let's go ahead and take a look at what those look like. Propanoic acid is a 3-carbon carboxylic acid, looks just like this. Methanol, right here, CH3OH, that's our alcohol. When they come together, they're going to produce water. And on this single bond oxygen side, we have the methyl group. And over here, we have 1, 2, 3 carbons from the propanoic acid. To name it, we would call it methyl propanoate. And again, we'll talk more about this. But sometimes it's really easy if you think about this as a tale of two halves. So for example, on this side, we have the carboxylic acid half. And on this half, call this the alcohol half. So when they come together, they form an ester that has part of it from the carboxylic acid and part of it from the alcohol. Okay, let's go ahead and take a look. This is how we're going to name these esters. The first word in the name indicates the alkyl part of the alcohol. So here we've got our carboxylic acid, and here we've got our alcohol. Since this was from methanol here, we only have one carbon here, so that's a methyl group. So methyl is going to be the first name in our ester name. The second word is the carboxylate name of the carboxylic acid. So if we split it here, we can see that we have a 1,2 carbon carboxylate. And in that case, it'd be ethanoic acid, which would form ethanoate. So we take the first word, methyl, the second word, ethanoate, we bring them together, methyl ethanoate. So these are all IUPAC and common names here. So we do see that, for example, ethanoate becomes acetate and propionate. We're not going to worry about those. The one that we do need to know is benzoate, right? Remember, this is benzoic acid. So when it's in an ester form, it's going to be called benzoate. Okay, so we're going to go into a little deeper dive on salicylic acid in particular because it's so important. So salicylic acid, that's what we were talking about at the beginning. That's this compound right here. Again, very irritating to the stomach line. However, if you form an ester by boiling this with acetic acid with a proton catalyst and heat, you actually form an ester called acetyl salicylic acid. Now, you don't need to write down the structure or anything like that. Just pointing out that by forming an ester here, that changes the structure. And because of that, it actually leads to a less irritating compound that's very useful still for pain relief, known as aspirin. Okay, so there's other ones. For example, oil of wintergreen is methyl salicylate. That's got the wintergreen flavor for skin ointments that easily passes through the skin, and it produces heat to soothe sore muscles. So it's a common flavor for, or a common aroma for various like salves and like icy hot, for example. So salicylic acid can also be used as the carboxylic acid part of an ester. So by heating it with methyl alcohol and a proton catalyst, you end up with methyl salicylate, which is known as oil of wintergreen. Okay, so let's go ahead and name this ester here. So we've got here an ester, and I want you to give it your best shot to name it. I'll let you pause if you feel like you're comfortable. If not, I'll show you how I do. Okay, so let's go ahead and take a look. So again, what I like to do is I like to split it up into halves. On this side, we have the alcohol half, and I can see 1, 2 carbons from alcohol. So that would be ethanol. So that means it's an ethyl group. Over here, we can see we have 1, 2, 3 carbons from the carboxylic acid. That would be propanoic acid. But remember, we're not worried about propanoic acid. This is now the carboxylate version. So propanoate. Bring it together. That's ethyl propanoate. Yeah, no problem, right? Okay, so let's clear those up and let's take a look. Yeah, ethyl on the other side, propanoate on that side. And now you're ready to go ahead and give me a IUPAC name for this one here. And don't worry about the common name. I only worry about the IUPAC name. This one in particular is responsible for the flavor and odor of pears. So go ahead, pause the video here. And when you come back, we'll take a look at the answer. So pause. Okay, so let's go ahead and take a look. So as always, we go ahead, draw a line here. We've got 3 carbons here, so that's a propyl. And then over here for the carboxylic acid half, it's 1, 2 carbons. So that would be ethanoate. So it should be propyl ethanoate. Oops, sorry. Or propyl acetate would be the common name. Oops, geez, I'm messing this up. Here's clear those. Okay, there we go. So again, propyl on the alcohol side, ethanoic acid on the carboxylic acid side, that becomes propyl ethanoate. Okay, next up. Esters are really important as components of fruits. So fragrances and perfumes from flowers and from fruits are largely due to esters. The thing is that the smaller esters are very volatile. That means that they evaporate really easily at room temperature. So they get into our nose, and that's how we can smell them. They're also soluble in water, and that leads us to be able to taste them. So for example, propyl ethanoate that we talked about, that's responsible for pears. Pentyl ethanoate is responsible for banana flavors. Octyl ethanoate, oranges. Ethyl butanoate is pineapples. And pentyl butanoate is apricots. So that's what leads to these different flavors that we can smell. And this is also why it's common to find like artificial fruit flavors, because you can easily synthesize these molecules as well. Okay, so why don't you go ahead and give it a shot? We've got a couple different formulas here, one for a carboxylic acid and another for a ester. But give me the condensed structural formulas for these compounds, and let's take a look. So go ahead, pause the video here, and when you come back, we'll take a look at the answer. So pause. Okay, let's take a look here. So 3-bromobutanoic acid. Well, butanoic acid is a 4-carbon carboxylic acid. So that's easy enough. You draw a carboxylic acid, that's carbon 1, 2, 3, 4. Then it has a bromo on carbon 3. So just count carbon 1, 2, 3, bromo, boom, you're good to go. Now, how about ethyl propanoate? Well, propanoate is the carboxylic acid half, right? So that's 1, 2, 3 carbons with a carbonyl and an oxygen bonded to it. Then ethyl tells you that you have a 2-carbon chain off of that oxygen that's bonded to the carbonyl. So CH3, CH2, C. Now this is double bonded to an oxygen, single bonded to another. That oxygen is then single bonded to an ethyl chain. Okay, so now not only can you form esters using acid and heat catalysts, but actually, as you'll see here, this is an equilibrium process. So you can easily actually hydrolyze esters as well. So acid hydrolysis is basically where ester will react with a water molecule to split up the halves. In other words, it goes back to a carboxylic acid and an alcohol. So in this case, for example, methyl ethanoate here can react with water in the presence of acid and heat to form its carboxylic acid half, that's ethanoic acid, and the alcohol half, methanol. The water molecule provides both the OH group that's needed and the hydrogen. But note here that you need an acid catalyst and heat to carry on this reaction. Okay, now if you want this reaction to go, you'll put a bunch of water in here. Adding more water by Le Chatelier's principle is going to make it so that these split up. Whereas if you were to remove the water, that's going to cause these two to actually click together. Now, that's not the only way that you can do it. You can actually also use a base to break up a ester. So base hydrolysis, which is also known as saponification, is where you take an ester compound, react it with one equivalent of a strong base, and heat it. And what happens is, rather than forming carboxylic acid, because you have a base component here, instead what you do is you form a carboxylate salt. So the carboxylic acid now is the carboxylate salt. In this case, you have ethanoic acid, comes ethanoate. Sodium is your counter ion, that's sodium ethanoate. The alcohol is still formed just like normal. So methanol is still your product of this saponification. Now, saponification is so named. Sapon is like soap, basically, and fication means making. This is a big process of soap making. So we'll talk more about that when we get to the fatty acids, what soaps are and how they work. But I think that's in the next chapter. But for now, that's what saponification is. Okay, so go ahead, try this out. Give me a balanced chemical equation for acid hydrolysis for methyl acetate, and then a base hydrolysis or saponification for methyl acetate. Pause the video, take a look at your notes, and when you come back, we'll look at the answers. So pause. Okay, let's take a look here. So first up, when you take an ester and react it with water, heat, and an acid catalyst, that is acid hydrolysis. That's where this ester is going to split up into its constituent, carboxylic acid and alcohol. In this case, acetate, which is ethanoate, right? That's the 2-carbon carboxylic acid. Methyl, the methyl part here becomes the methanol as part of the products. Now, for base hydrolysis, on the other hand, we don't form the carboxylic acid. Instead, we form the carboxylate salt using the counterion from the base. So this ethanoic acid becomes potassium ethanoate, and you're left with the alcohol, in this case, again, methanol. So again, just pointing out the key differences here. When we use an acid catalyst and heat, we know that we're going to form the carboxylic acid and the alcohol that make up our ester. But when we use a base instead, what happens is we form the carboxylate salt of that carboxylic acid, and the alcohol is formed like normal. Okay, that does it for today's lecture. So make sure to ask any questions that you have in the comments down below. We have one more lecture for this chapter that's going to cover amines and amides. So I'll see you soon. Until then, bye-bye.